In this video we are going to talk about hyperbolas. Right, so consider the function r of t which is equal to a tan t and b sec t, where t is from minus pi over 2 and 3 pi over 2, and t is not equal to pi over 2. So if we've got a function like that and t is equal to pi over 2, we have a problem. Go and look it up if you don't know what the problem is. Where a and b are positive constant real numbers. So what we want to show is that x will be in the range of c of r if and only if y squared minus over b squared minus x squared over a squared is equal to 1. And then we are also going to then sketch the curve, and then we will look at a concrete example with values for a and b. Right, so consider a point x that is in c. Then x is in r of t for some t between minus pi over 2 and 3 pi over 2, where t is also not equal to pi over 2. So that so if we take y squared over b squared minus x squared over a squared, and then we substitute what we have for x and y, we then see that that is just sec squared t minus tan squared t is equal to 1. So it satisfies that. So we want to take that and then show that x has to be equal to that and y has to be equal to that. So let's take a point x, so that y squared over b squared minus x squared over a squared is equal to 1. So yeah, we want to show that x should be in C. So we have y squared over b squared is equal to 1 plus x squared over a squared. So that is greater or equal to 1. We just took that on the other side, and then we know that because this one is greater or equal to 0 at all times, 1 plus that becomes greater or equal to 1. And so y over b is always greater or equal to 1, or y over b is less than or equal to minus 1, right? And this is because if it's minus 1, if we square it, then it becomes 1, right? Or if it's less than minus 1, if we square it, then it becomes greater than 1, right? Satisfying this. So we have, in this one, we've got 4 cases that we need to deal with. So I think we will deal with 2, and then the other 2 will follow in a similar fashion. So there are 4 cases to consider, namely y greater than b and x greater or equal to 0. So y greater or equal to b and x greater or equal to 0. Y greater or equal to b and x less than 0. Y less than or equal to minus b and x greater or equal to 0, and y less than or equal to minus b and x less than 0. So we are going to look at 2 of those cases, and then we can then deduce the rest from that. So suppose y is greater or equal to b and x is greater or equal to 0. Then the function b sec t is continuous on 0 to pi over 2, and its range on this interval is from b to infinity, right? Right, and then so therefore there exists a real number t between 0 and pi over 2, so that y is equal to b sec t. But we know that y squared over b squared minus x squared over a squared is equal to 1, so that we can then say x squared over a squared is equal to b sec squared t minus b squared minus 1, which is equal to sec squared t minus 1, and we know that that is equal to tan squared t. Now, since x is greater or equal to 0 and tan t will be greater or equal to 0 for any t that you pick from 0 to 2 pi, it follows that x is equal to the positive of a tan t, right? And hence x is going to be equal to a tan t b sec t, which is what we know to be r of t, which is equal to c. So here we found y first, and then we found that x is that, and therefore it means that x is in c, right? So that case is done. Now let's look at the second case. Now suppose y is greater than or equal to b and x is less than 0. Then the function b sec t is continuous on minus pi over 2 up to 0, and its range on this interval is b up to infinity. So since y is greater or equal to b, it once again follows that there exists a real number t between minus pi over 2 and 0, so that y is equal to b sec t. Then we use our equation to find out that x squared over a squared is equal to tan squared t. Now, because we are looking at the case where x is less than 0, and then we also know that tan t is less than or equal to 0 for the for this case from minus pi over 2 up to 0. Therefore, x will be equal to the minus of minus tan t, which is just the positive of tan t. And so therefore what it means is x is a tan t. We know that y, we showed that y was tan t, sorry, was b sec t. So therefore x, which is a tan t b sec t, is equal to r of t, which is equal to, which is an element of c. So therefore we have shown that for this case x is also in c, right? So for the two remaining cases, they follow in a similar way. So if y is less than or equal to minus b and x greater or equal to 0, then there exists a t between pi and 3 pi over 2, so that this happens. And if y is less than minus b and x is less than 0, then there exists a t which is which is between pi over 2 and pi, so that x is in there. And this is given as exercise 5.15, 5.1, number 5 in the exercises of the textbook. So now sketching the curve. Right. So note that y squared over b squared minus x squared over a squared is equal to 1. If and only if. So if we express y in terms of x and a and b, we get this, right? So we've got a positive and a negative. So we're going to separate them. So the curve therefore consists of two branches, C1 and C2, corresponding to the positive and the negative square roots respectively. So we consider the branch C1 where the y is positive, right? So for the positive, if we want to find the turning point, the turning point is when x is equal to 0. We just differentiate that, equate to that to 0, and then we find out that x is equal to 0. If we do the second derivative to check if it's concave upwards or concave downwards, we see that the second derivative is positive, and so therefore the curve is concave upward. And now we want to check the tangent. So if we look at the limit as x tends to infinity, oh no, sorry, not tangents, asymptotes. So if we check the limit as x tends to infinity, we see that that is equal to infinity. And then the lines with equations y is equal to b over x and y is equal to minus bx over a are asymptotes of C1, right? Right, and we can see that for the positive one, b over the square root of that over a is greater than bx over a, which is for any x that you pick that is greater than 0. And again, b of x is also greater than minus bx over a for x that is less than or equal to 0. So therefore, we have that the limit as x tends to infinity of that minus bx over a is equal to 0. And this is exercise 5.1 and number 6 in the textbook. Right, and in the same way, the limit as x tends to infinity of that plus that is equal to 0. So therefore we can then sketch the branch C1 of the curve, and we find out that the these are the asymptotes. We have shown here that these by finding the limits here, we find out that these are what the asymptotes. The curve doesn't get to y is equal to minus bx, but we have shown just now that the limit is 0 well, with the difference. So it approaches uh, this curve and it approaches that curve, but it never touches it. So therefore, that means that those are asymptotes, right? These two, right? So same story for C2. So note that the branch C2 of the equation, with the equation the negative there, is just a reflection in the x-axis. That is, xy is in C1 if and only if x minus y is in C2. So now, so we can then sketch the graph, and then so we extend these asymptotes, and then we get that as the other part of the equation of the curve. So we get this, and this is what is known as a hyperbola. So consider the vector function r of t, which is all that. So in example 5.1.14, it is shown that the range of r is the curve with the equation that, and this is what is known as a hyperbola. And we are going to talk about some things that we note for a hyperbola. So the hyperbola consists of two branches. So if xy is equal to rt with t between minus pi and pi over minus pi over 2 and pi over 2, then y is greater or equal to b. And if xy is equal to r of t with t between pi over 2 and 3 pi over 2, remember this is defined for these points. So 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 the subdivision is there like that. Then y is less than or equal to minus b. On each of the two branches, the point r of t moves from left to right on the curve as t increases, right? um, so we can see that as t increases, we are going from left to right, right? And they're from left to right. So the hyperbola C is symmetric about the x-axis. So if we look at that, then we just see it's a reflection. So uh, and also about the y-axis. So if we look at from the vertical point of view, that is reflected there, that is reflected there. So therefore, they are symmetric. And the y-axis is the major axis of C. So where the curves are. So if they were looking that way, then x would be the major axis. The other point, the hyperbola with equation y squared over b squared minus x squared over a squared is equal to 1 can be described in the following way. So we are going to do what we did for ellipse. So suppose c is the square root of a squared plus b squared. Then it can be shown that c, um, which is the set of all points, which is the absolute value of the norms of x minus 0c, the norms of x minus the norm of x minus 0c minus the norm of x minus the vector 0 minus c. So if we take the absolute value of that, it is going to be equal to 2b, and then it is illustrated here that if we do that, so if we take the points there, 0c and 0 minus c, and then if we calculate the if we add L1 and L2, or at least the size of L1 and L2, then we get 2b. Yes, so the absolute value of L1 minus L2 um, is equal to 2b. Right, and the points 0 minus c and 0c are called the foci of the hyperbola C, and we call the points 0b, 0 minus b the vertices of C. So these ones are the foci with the dots there, and then this point and that point are the vertices of the hyperbola. Right, and the vertices in this case are defined to be um, the points that are closest to each other, right? So you'll see that the points that are closest to each other are these ones. Well, looking at the different branches, right? This will be the closest, right? So therefore, okay, so let's look at other points. So number 4, recall that example 5.1.414, that the lines with equations y is equal to b over ax and y is equal to b minus b over ax respectively are the asymptotes of the hyperbola C, right? So we saw that we had these asymptotes, right? And if p is equal to p1, p2, and then we add that point to what we have, r of t plus p, then that means we can then shift our hyperbola same way as we did for an ellipse. So we get that kind of an equation. And A, the foci changes from P from 0C to P1 and then P2 plus C, and then P1, P2 minus C. Those become the foci of E. And then the vertices move from 0b and 0 minus b to p, p2 plus b, p1, p2 plus b, p1, p2 minus b, right? So we've just shifted it um, with p, right? And then the lines with equations b over a, and then instead of having x minus 0, now we've got x minus p1 plus p2, and then instead of having minus bax, now we've got minus ba x minus p1 plus p2 will become the asymptotes of E, right? And then to illustrate all that information, um, we've got that graph, right? So you see the asymptotes are there. Sorry, so they've been moved from the center here, from the origin here. We've shifted there, and then now we've got all that. So, and then we've got our vertices and the foci here, right? So that is how we shift the hyperbola from the center to y is equal to we shift it by p1 p2, right? And then this hyperbola is symmetric about the lines x is equal to p1 and y is equal to p. In the first instance, when we looked at the first example, it was symmetric about the x-axis and the y-axis. So x is equal to 0 and the equation y is equal to 0. So now we've shifted it to x is equal to p1 and y is equal to p2. Right, I think this is the last point, maybe not. So let v of t be equal to b sec t and a tan t, where we've got those conditions. Then a point x is in the range of k of v, if and only if this happens, and the curve is a hyperbola. So here, notice that instead of having a tan t here and then b sec t there, we've moved it, so therefore it rotates, or yes, it rotates like 90 degrees clockwise or anti-clockwise. It's the same thing, and then everything just shifts like that, and then the information will be the same. So here, instead of having the asymptotes as x is equal to b over ax, we then make y is the subject of the formula, and then it changes like that, right? Okay, we make x the subject of the formula, and therefore, because we are looking at its inverse, then therefore we then say y is equal to a over bx, and then y is equal to minus a over bx. So we just, where there was an x, we put a y, and where there was a y, we put an x, basically for pretty much everything, and then it falls into place like that. So that is what we have. So we're going to look at an example, and then that will be it for this video. So we sketch the curve C with equation x minus 2 squared over a quarter, and then minus y plus 1 squared is equal to 1. And then we want to indicate all axes of symmetry, turning points, vertices, and asymptotes. So consider the hyperbola. So we start off with the one that is on the origin, which is centered on the origin, and then we get that it looks like that, and then we can deduce that x is in C if and only if that is equal to 1, and that is if and only if x minus 2 and then y plus 1 is in H, right? And then so therefore x is in C if and only if x is equal to y plus 2 minus 1 for some y in H. And the H here is talking about the one that is centered on the the one that is centered on the origin, right? So we then move it. So minus 2 tells us that we have to shift it uh, 2 units to the right, and then that one 2 units downwards. Oh, is it? Yes, downwards, right? Yes. So to the right and then downwards. So then we get that. So therefore we obtain C from H by shifting E 2 points to the right and then 1 unit down, right? So the turning points of H um, are at minus a half 0 and minus half 2. Therefore the turning points, then we add that point 2 minus 1 on the points that we what on these points, right? And then we get minus 3 2 minus 1, and then 5 over 2 minus 1. And then the axis of symmetry of H are the x-axis, that is the lines x y is equal to 0 and x is equal to 0. Therefore the lines y is equal to minus 2x and y is equal to 2x become the new axis of symmetry, right? So therefore the asymptotes of C are the lines with equations uh, y is equal to minus 2x minus 2 minus 1, and then 2x minus 2 minus 1, and then we get so we get those two equations as the asymptotes. And so therefore with that we are able to then sketch the graph um, of our hyperbola that has been shifted, right? So therefore we get something like that. So we get our asymptotes like that, and then we've got our axis of symmetry, these ones, and then we've got the foci, and then oh, we didn't put the foci. The foci is not here. We've got the vertices there, like that. So therefore that is all about a hyperbola. Thank you. We'll continue with uh, chapter 5.2 in the next video.